So welcome to this video. In this video, I'm going to talk about the idea of synthesis, that is, producing music artificially, starting with electronics. And in order to motivate that, I want to just quickly review what we talked about in the last video about converting between actual sounds back and forth between those and electrical signals. And so, if you remember from last time, we talked about how the basic function of a microphone is to capture a sound wave and transduce it, that is, convert the information about the sound wave into an electrical signal. And so that worked by this process of electromagnetic induction when you have a dynamic microphone. So the sound wave is incident upon some kind of a membrane. That the pressure in the sound wave causes the membrane to move, and then that causes the motion of a magnet relative to a coil of wire. And then this electromagnetic induction effect means that we're going to induce a current in the wire that moves one way when the magnet moves one way and moves the other way when the magnet moves the other way. And so in that way, we managed to capture the information about the time graph of the sound wave into an electrical signal. So that time graph now represents the electrical current in a wire. And we talked about how most recording today basically just takes that analog electrical signal and samples it. That is, it looks at the amplitude or the value of the graph at certain specific times and just records those list of amplitudes as a set of numbers in your computer memory. So that would be with an analog to digital computer. And then you can just store this set of numbers as a WAV file or compress it to an MP3 file and play it back whenever you want. So the playback basically works in the opposite way, where you take this list of numbers, send it through some electronics called a digital to analog converter, and that produces an analog electrical signal that is hopefully exactly the same as the one that you originally used to produce the digital recording. And now you can send that to a speaker or your headphones and you're hearing the music again. Okay. And just to remind you, the way that that works, converting between the electrical signal and the sound wave, it's just the opposite of that dynamic microphone, where again you have a coil and you have a magnet and you're sending the electrical signal through the coil, and when that current goes back and forth, that coil acts like a magnet, so it's an electromagnet, so it will attract or repel the permanent magnet, and through this the membrane of your speaker ends up moving back and forth, and that produces the sound wave. So the idea of synthesis is just basically to produce music, but skip that very first step where we actually had the real instrument or the real voice that was being recorded with a microphone. So the idea of synthesis is that it's going to be a purely electronic sound production. And so what we're going to do is either start with some relatively simple electronics to produce an electrical signal, produce something like an analog current that's going back and forth and then becomes our sound wave when we send it to the speaker. So that's analog synthesis, where the first step is producing this electrical current. Or in digital synthesis, we use a computer to produce essentially what would be a digital recording, except we're just generating it from scratch. So we produce the sound digitally first, then convert it to an analog electrical signal, then send it to the speaker. So these are the two main types of synthesis. Both of those are used today quite a lot. So I'm not really going to distinguish too much between these two in the rest of the video. I'm going to talk about how the actual waveforms for the synthesized sound are built up. And this process works in the same way in analog and digital synthesis. The difference is just that in analog synthesis, we're using specific electronic components to achieve the synthesis, whereas in digital synthesis, it's basically computer programs that are manipulating this sound file. Okay, so how does it work? Well, generally, we're going to start with some basic waveform. And so we would take a waveform, choose a simple shape like a sine or a triangle wave or a square wave or a sawtooth. I'm going to talk more about these things coming up. And we would just choose the pitch or the frequency that we want as the basis of our sound. The next thing is we take that sound and then, kind of like we talked about with the human voice, where the sound from our vocal folds is then processed or filtered by our vocal tract and by the shape of our vocal tract. In most synthesis, we're going to take our basic waveform and then we're going to filter that spectrum in some way. So these waveforms are going to be a combination of a fundamental tone and harmonics, and we're going to suppress certain harmonics and emphasize other ones. And so this is a spectral filter. So the combination of these two steps will produce our basic tone with a certain pitch and a certain timbre. And so far that's going to be just a continuous tone. And what we want to do then is shape the time graph. So we're kind of going to filter the time graph now, so that instead of just being a constant amplitude or a continuous tone, maybe it takes a little while to start when you press a key on your keyboard. It takes a little while for the sound to come to its maximum volume, and then it decays, and when you take your finger off, it gets quieter in a certain way. Okay, so we're going to basically shape the loudness in a certain way, and then the combination of all of those things would be a tone that has a certain timbre, and it comes on in a certain way and it turns off in a certain way. Okay, and we could do fancier things as well. We could have a time-dependent filter so that the timbre is a little bit different at the start of the note compared to the middle, compared to the end. We could do various other things with the loudness or the frequency, so we could have those oscillate with time. And we could add extra effects, things that you've probably heard of: chorus, reverb, vibrato. So this is a basic summary, and in the rest of the video I want to go through each of these steps in more detail and then give you some examples of manipulating the actual sounds. Okay, so our starting point then is just a basic waveform. And so in an analog synthesizer, we would just have some electronic device that produces a current with this waveform. So the simplest thing we've talked about is just the sine wave, or the waveform for a pure tone. The spectrum is super simple. It's basically just one frequency. And so that would be the most basic thing you could imagine with synthesis, that you just take a sine wave and then maybe add to it another sine wave and then add another and add another. And so this is the idea with additive synthesis, where you could build up your sound just using these really simple sine waves, or just using the really simple pure tones. And so actually the very first synthesizers operated in this way. The telharmonium that I mentioned in a previous lecture was this gigantic device that managed to achieve this. And then later the Hammond organ was based on this idea, and still is. And so just want to give you an example of that. So with the Audacity program, one of the things we can do is actually generate sounds. And so what I've done here is I've already set it up to generate a set of pure tones. And this first one is the frequency of 100 hertz, and then The second one is a frequency of 200, 300, 400. So these are all harmonics of that lowest frequency. And so just to show you how to do that, I will generate one more pure tone in the last column. So when I do that, click the generate, and again, I'm going to choose sine, and I'll make this one a frequency of 500 hertz and an amplitude of 0.5. Okay, and so that, then it's zoomed out again, but if we zoom in, then you can see that that's added one more sine wave onto our track. So we've got now 5 different sine waves that are going to all add up. So first, let me actually play those separately so you can hear what they sound like separately. That's the lowest one. That's the next one. Okay, so hopefully you could hear all of those. And so now what I'm going to do is actually put them all together. And so we'll hear what it sounds like when they're all together. Okay, so that has that's a tone with a frequency of 100 hertz, but it has a different timbre than before. It sounds a little bit like a Hammond organ. So that's no coincidence, because basically this is what that organ is doing. Now, in most synthesizers today, what you're doing is actually starting from a more complicated spectrum. So instead of starting with just pure tones or just sine waves that have this really simple spectrum and adding a lot of those up, which, by the way, you should be able to do in order to get absolutely any sound, because we've understood that any sound could be a combination of pure tones with different amplitudes. So you could do that, but it turns out that it's easier in some ways to produce useful and interesting sounds by starting with a more complicated sound and then filtering it or getting rid of some of those harmonics. So this is the idea of subtractive synthesis, where we might start with something like a square wave. So you see, if you look at the spectrum of a square wave, then it has all of the odd harmonics. So a 100 hertz square wave would also have some 300 hertz pure tones, some 500 hertz, 700 hertz, and so forth. Or even more complicated than that is the sawtooth wave. And that one includes all of the different harmonics. So 100, 200, 300, 400, and so forth. Actually, certain synthesizers start with something even more complicated, which would be an actual sound, an actual sampled sound that you record, and then you build your synthesis off that. Okay, but I'm going to talk about these simple cases, so the square wave, the sawtooth wave. And those are things you could also select in Audacity when you choose the generate tone feature. But what I wanted to do is actually just show you on a different synth. So this is a free synthesizer that I downloaded. You can find many different varieties of synthesizers that are free on the internet, or other ones that are more complicated and interesting. So here you notice that one of the basic things is you get to choose a waveform. So that's the starting point. So you can have the sinusoidal wave. But I'll just play the other ones to let you see how they sound. So the next one is actually a triangle wave. That's a sine wave, and that has a few odd harmonics on top of the sine wave, but they fall off in amplitude very quickly as you go up. So that sounds like this. And then if we go to the square wave, so again, this is all the odd harmonics that fall off in a particular way. finally we can go to the sawtooth wave. Which has the richest spectrum in terms of the harmonics. Okay. One of the most famous synthesizer lines of all time was the Axel F theme from Beverly Hills Cop. So you probably heard that. It's made various comebacks over the years. That one was actually almost just a sawtooth wave synthesizer. Okay, so what do we do with those sounds? So, that's 3 different sounds that we could have by choosing our basic oscillator. And what we can also choose about those sounds would be the pitch and also how loud they are. Okay, so that's the first thing. But then what we want to do is shape that sound into something different. Just like when we were talking about the human voice, how we can shape our voice into different sounds, make different vowel sounds, starting from the same sound that's coming from our vocal cords. So the way we do that, the simplest way we can do that is by using what are called filters. And so these act on the spectrum. You should think of the filter as modifying the spectrum by reducing certain harmonics and enhancing other harmonics. And so every filter is specified by a specific shape, the specific shape of the filter. And the shape is it's a graph in frequency space. So here's an example where I have a filter that is going to let through, or basically not change, any of these low frequencies below 2000 hertz. But then anything above something like 2500 hertz, anything above that is going to be not passed at all. So it just gets rid of a whole lot of the high harmonics. And so that would take this kind of graph for our sawtooth wave and give us this spectrum graph in the end. Let me just do this. So I'm going to do this in Audacity to show you, and then I'll do it on the synthesizer as well. Okay, so first let's get rid of a few of these tracks. So I'll just show you how to filter in Audacity again. So we'll generate a tone. We'll choose sawtooth. I'm going to take a frequency of 200 hertz and an amplitude of 0.5, and we'll let that play for say 2 seconds. Okay, so there it is. And so we get to hear that just plain sawtooth wave. And now if we want to filter that, we go into Effect, Filter Curve, and let's flatten it again. And so we could just choose some points to control here. And so I'll just do the one that I showed you on the slide. And so this is a filter that just lets everything through up until 2000 hertz, and then it very quickly falls off to 3000 hertz. Okay, and we can preview that and hear what it sounds like. Okay, so you hear it's a little bit smoother than that sawtooth sound on its own, and that's because a lot of those high frequencies have just been eliminated. Okay, so it's exactly this one that I've shown in the spectrum graph on the right here, where we really only have 4 harmonics and a little bit of the 5th harmonic. So if we go to the actual synth, so you'll notice that over here we've got a filter. And so this is a filter of the type that I was showing, where it lets through all of the frequency up to some cutoff frequency, which we can control. And so let's just hear how that sounds. So this is the plain old saw wave. Now I'll turn the filter on, and if I bring down the cutoff all the way down, then you just have the just have the pure wave, and then as I add more, okay, so you hear how the timbre of the sound changes as I allow more and more higher harmonics to come in. Okay. So let me just mention a few different kinds of filters that you could have. So you saw that in Audacity, I could pretty much make any filter shape I want. I could control things. I could come up with something very complicated. So when we were talking about the human voice, we said that the vocal tract does a filtering something like this when it wants to produce an ah sound. And actually it's interesting just to use that same filter for a sawtooth wave and hear what it sounds like, because it's actually a little bit like an ah sound, but in this case completely artificial. Let's hear that. So as compared with this. Okay, so putting the ah filter on, it does have a little bit of that characteristic. Okay, and just for fun, let's do the E filter. Okay. Okay, so in this synthesizer, we pretty much just have one choice, or actually two choices, two parameters that we can control. So that would be the most common kind of filter, the one that I showed in the last slide, the one we used in that synthesizer. It lets through the low frequencies, so it lets them pass, and it doesn't let the high frequencies pass. So it's a low pass filter. The opposite of that would be letting just the higher frequencies go through and not letting the lower frequencies go through. And that's what would be called a high pass filter. And then if you wanted to take out low frequencies and high frequencies, so that would be like a combination of low pass and high pass. And so that's called a band pass filter, where there's a certain range of these frequencies that you're going to be keeping. And one other kind of filter, or a variant of the low pass filter that you'll see a lot, is a filter with what's called resonance. And that means that at this cutoff frequency above which you're not passing much sound, you actually enhance you actually have this bump here. So you actually enhance the harmonics at that particular frequency, or in that little range of frequencies. So I just want to let you know what that sounds like. So that's this resonance parameter here. So we'll just hear what that sounds like if I increase that. Sorry. Okay, and then I can adjust the cutoff frequency as well. All right. So you hear that extra little punch of high frequency sound right at the cutoff frequency. So far, all these things that I was talking about basically affect the continuous sustained tone that I would get if I keep my finger on the key. But now I want to talk about how to affect the overall shape of the sound in time. And so that's done through what is known as an envelope. So the envelopes are basically like shapes that change the time variation of our tone. So if you have a real musical instrument and you look at what does the note look like if you were to record it, let's actually do that with something here. Okay, let's take our harmonica that I happen to have sitting here, and I'll just record a note that I actually play on the harmonica. Okay, so that would be one different way of playing it. And so you see that it's not really just a continuous sustained tone. When I played that note on the harmonica, takes a little while to get up to its maximum amplitude, and then maybe it stays there for a little while, and as I decreased my pressure, my breath pressure on the harmonica, then the shape of the tone, the amplitude of the tone fell off. And so generally notes from musical instruments are characterized by some shape like this. And in the world of synthesis, we kind of divide that into discrete parts. So the most common division of parts of a note that you'll see is that we talk about the attack, which is the phase where you're getting up to the highest amplitude, the decay that happens right after that, where it's decreasing down to the sound that you're going to have if you just keep your finger on the note, on the keyboard note. And then finally, when you release the note, when you release your finger from the keyboard, then it doesn't immediately stop. It decays a little bit. Okay, so these are standard parameters that you see in pretty much any synthesizer, and I just want to demonstrate that with the one I have here. So this is kind of nice because you actually, instead of having knobs for those 4 different parameters, you can actually just move around these green, red and yellow and green circles. Okay, so you can go from this shape, which is the sound immediately goes to its maximum volume, stays there, and then immediately turns off as soon as I release the key. So let's change it a little bit so it takes a little bit of time to get to the maximum volume. And then maybe it drops off a bit from that. And then maybe when I release the key, it takes a little bit for the sound to drop off to 0. Okay, so let's hear the difference. Okay, so that's just, again, the same sawtooth wave that we started with. I turned off the filter, and just by changing the envelope for the sound amplitude, we have a very different sound. It actually sounds a lot more like strings. You could play, this was another classic synthesized theme from the 1980s. You might recognize. So that gives you a lot of control, again, over about how the note's going to sound. So that would be mostly affecting how it sounds at the beginning and how it sounds at the end. There's another type of envelope that I'll mention that's very common, which is called the low frequency oscillator. And this is going to affect how your note sounds during the sustain portion. So this low frequency oscillator is just an envelope shape that is some kind of an oscillating wave. It could be a sine wave or a square wave or sawtooth. And so what you could do is, for example, apply that as a filter to your time graph, so that instead of something like this, you'd end up getting something like this. Okay, so that's what these envelopes do. You just specify a shape, and then you apply this as just like a filter for the time graph, and so it affects the overall shape of the amplitude. Okay, so this is a good example. So you get your envelope, you got your waveform, and then the resulting thing, in this case, it's oscillating up and down in terms of the amplitude. So that would be a tremolo effect. So on this synthesizer, we see that right here, you can choose to turn on this low frequency oscillator. We can choose the shape of that. We can choose how quickly it oscillates, and we could choose the depth, so how much the oscillation is, and we can choose which parameter is changing. So I'm going to try just the overall volume of the note, and so we'll hear what that sounds like. Okay, so there you heard the tremolo effect. I could also use that low frequency oscillator on the pitch. and let me maybe not quite have as much variation. So this should give us a vibrato effect. Remember, the time variation of pitch is vibrato. Okay, so again, all that was our sawtooth. We applied the envelope, and now we've put this envelope also on the pitch and had that vary with time. Okay, so we could do more complicated things. So as I just showed you, I used a low frequency oscillator not on the overall amplitude, but actually on another parameter, the pitch. And similarly, we could use an envelope like this to control a parameter like our filter. So we might control something else. And in the synth, you notice that you could just choose which parameter you want to control. So, and in fact, for the filter in particular, you can actually select how you want that filter to be applied. So I can change the filter envelope here. And so just like the volume turning on and turning off in this way over here, in this case, you would start with a plain sawtooth, and then the filter would come on, and it would follow this particular shape. So how strongly you filter out those high frequencies is going to be determined by this filter envelope. Okay, so let's actually hear what that sounds like. So this is, and then with the filter. Okay, that had a lot of the resonance there. So that was an interesting modification. And you're probably getting the idea that there are just an infinite number of things you could do in order to play around with the sounds. And this is true. So I just want to mention one more thing before we finish here, just because it's a really common effect. And it's actually interesting to understand the physics of it. And so this is what's called reverb. So reverb is something where you're trying to replicate the sound of a musical instrument or the sound of music that is being produced in a specific kind of space. Okay, so if you were to go and play your saxophone outside, it's going to sound different than if you play it in a room or in the shower or in a cathedral or in a concert hall. And the reason is that when you play the note, in the case where you're just outside, well, the sound just goes out and it doesn't come back. But if you're in a room, it's going to bounce off the walls, come back to you, bounce off other walls, come back, and it might bounce around for a little while before it finally goes away. And so basically what reverb does is it tries to recreate that effect. So to understand the modification that we do in order to produce this reverb, it's actually simplest to think about the digital waveform. So think about the waveform as being this pulse of sound at a specific amplitude happening at all these different times. So let's imagine that we just had one almost instantaneous pulse of sound. And let's say we did that in a specific environment, like a cathedral. So that pulse of sound would then reflect off all the different surfaces, and we could record what the sound is that we would actually hear starting from that initial pulse. And so it might look something like this. Maybe there's a pulse, and then a little bit later there's another pulse, and then a little bit later there's another one, and then there's a bunch of smaller pulses as these things start bouncing around. And so the full sound from a single pulse might be this. Okay, so this is the sound that you would hear outside or in a room that had perfect sound insulation on the walls, and this is the sound in your particular space. And so what the reverb effect does is it basically just takes whatever sound you want to apply it to, and it does a transformation where it kind of replaces every one of these with something like this, and then it adds them all up again. And so the net effect is that your sound is just processed to include artificially what would be reflections from walls and resonance or reverberations in the chamber. Okay, so that is it for my basic summary of synthesis. Just as a review, what we do is start with some basic waveform that could be as simple as a combination of sine waves in additive synthesis, or one of these more complicated waves, the sawtooth or the square wave, or possibly a couple of those together. We would choose the pitch that we want the final note to have by choosing the frequency of this basic waveform. Then we're going to apply some filters to the spectrum, damping out certain frequencies and emphasizing others, so that will change the amplitudes of the various harmonics that we have in our note. So these two things determine the overall timbre of the note during the sustained tone that we want to produce. But then we also want to specify how is our note going to turn on, how is it going to turn off, and that we do through an envelope. So we just specify the shape of the overall shape of our waveform in time. And this idea of an envelope also applies to other parameters. So we could also imagine doing this filtering, but in a time-dependent way. Maybe the filter turns on only after a certain time or in a particular way. So there's a lot of different complicated things you can do with these various envelopes. Okay, and we talked about how there were ones that come on and turn off, and then also these low frequency oscillators that just oscillate in some way. And finally, at the end of all that, you could still choose from various sorts of effects like chorus or echo or reverb. And I talked about reverb and how that tries to replicate the sound that it would be in certain different kinds of spaces. Okay, so that's it for the video. Next time, what I'm going to talk about is light and vision and how that compares to our understanding of sound and hearing.